You think you understand gravity. Earth pulls you down. Objects fall. The moon goes around. Simple. Except it's not just wrong, it's fundamentally wrong. About what's actually happening. About what gravity actually is. Newton figured it out centuries ago. Right? Force equals mass times acceleration. Inverse square law. Beautiful mathematics. Perfect predictions. Case closed. No. Not closed. Not even close. Because gravity isn't a force. It was never a force. And one equation published in Annalen der Physik, November 1915, proves it. A century of evidence confirms it. The 1919 solar eclipse confirmed it. LIGO confirmed it in 2015. The Event Horizon Telescope confirmed it in 2019. Your GPS confirms it every single second of every single day. And when you finally see what gravity really is, when you understand what Einstein saw that Newton couldn't, the whole universe starts to look different. Not metaphorically. Literally. The ground beneath your feet. The moon above your head. The apple falling from the tree. None of it works the way you think. This is the story of one equation that changed how we understand the universe. And a century of evidence proving it right. Let me show you. Stand up right now. Feel your weight. You feel it? Right? That heaviness pressing you into the floor. Earth pulling you down. Gravity doing what gravity does. Except that's not what you're feeling. Focus on the actual sensation. Really focus. Your feet against the floor. The floor pushing up against your feet. That pressure you feel, that's not gravity pulling. That's the floor pushing. You have never, not once in your entire life, felt gravity pulling you down. Think about that. Every sensation you've ever called gravity is actually a contact force. The chair pushing against your back. The ground pushing against your shoes. The bed pushing against your body when you lie down. Always pushing up. Never pulling down. Not a pull. A push. From below. Every single time. And here's something even stranger. Right now, as you're watching this, the moon is falling toward Earth. Has been falling for 5 billion years. But it never arrives. Never crashes. It just circles. Always falling. Never landing. What kind of force does that? What kind of pull pulls for 4.5 billion years and never actually pulls anything in? Newton himself couldn't explain the mechanism. He called it action at a distance, a force reaching across 400 kilometers of empty space with nothing in between. And in a letter to Richard Bentley in 1693, he admitted this idea was, in his own words, so great an absurdity that no thinking person should accept it. But the mathematics worked. Predictions matched observations beautifully. So people stopped asking uncomfortable questions. They shouldn't have stopped. Go back several centuries. Nobody understood how planets moved. Copernicus had made the radical claim the planets orbit the sun, not the Earth. But he couldn't explain how. What kept them moving? What shaped their paths? He just said they go in circles. No mechanism. No reason. Then came Tycho Brahe. For over 20 years, from 1576 to 1597, Brahe did something nobody had done with that level of precision. He watched the sky, night after night, year after year. No telescope, those hadn't been invented yet. Just massive brass instruments, some over 2 meters tall, and an obsessive commitment to accuracy. He measured planetary positions to within 2 arc-minutes fractions of a degree that no one before him had achieved. Decades of data. Thousands of observations. All recorded by hand. You can't understand nature by guessing. You have to look. When Brahe died in 1601, his assistant Johannes Kepler inherited all of that data. And Kepler had a theory: planets move in perfect circles. Beautiful. Elegant. Makes mathematical sense. So he tested it against Brahe's observations of Mars. It didn't fit. Off by 8 arc-minutes. Now 8 arc-minutes is tiny. Most astronomers would have ignored it, called it noise, moved on. But Kepler knew Brahe's precision. Brahe's data was accurate to 2 arc-minute. An 8 arc-minute error wasn't noise. It was real. So Kepler did something extraordinary. He threw out his own theory. Circles gone. Started completely over. Years of recalculation. And what he found changed everything. The planets don't move in circles. They move in ellipses. Stretched circles. With the sun not at the center, but at one focus. Beautiful. But it raised a bigger question. Why ellipses? What force could produce that shape? Meanwhile, in Italy, Galileo was doing something completely different. Simple experiments with remarkable results. Rolling balls down ramps. Sounds trivial, but watch what happens. A ball rolls down an incline. It speeds up, reaches the bottom, rolls onto a flat surface, and it keeps going. Doesn't stop immediately. It slows down eventually, but only because of friction. The roughness of the surface, air pushing against it. Now imagine you could eliminate all of that. Perfectly smooth surface. No air. No friction at all. What would happen? The ball would roll forever. Same speed. Same direction. Forever. This bothered people. Deeply. Because everyone knew or thought they knew that objects naturally come to rest. You push something, it moves, it stops. That's how the world works. Motion requires a push. Take away the push. Motion stops. No. That's backwards. Motion is natural. An object moving in a straight line at a constant speed doesn't need explanation. That's the default state of the universe. What needs explanation is change. Slowing down, that's friction doing work. Speeding up, that's a push. Changing direction, that's a sideways force. Not motion requires a force. Motion is the default. Change requires a force. This is inertia, the first law of motion. And Galileo saw it clearly 3 centuries before anyone had the instruments to prove it perfectly. But inertia creates a puzzle, a devastating one. Planets should move in straight lines. That's their natural state. No force needed, just straight ahead, forever. But they don't move in straight lines. They curve. Their paths bend continuously toward the sun. Every second of every orbit bending, something must be deflecting them. Every single instant. Without stopping. What? Isaac Newton saw it clearly. Planets want to go straight. That's inertia. But they curve. Something is changing their motion. Constantly. At every point in their orbit, he called it gravity. A universal attraction between any two objects that have mass. Any two. Not just planets and stars, any two objects in the universe. The force depends on two things: mass and distance. More mass, stronger pull. Greater distance, weaker pull. And not just weaker, it drops with the square of the distance. Double the distance, the force drops to 1/4. Triple the distance, 1/9. With this one principle, everything fell into place. Why do planets move in ellipses? Because they're falling toward the sun while simultaneously moving sideways. The combination of falling inward and moving sideways, that's what creates an elliptical path. Kepler's laws, those patterns he spent years extracting from Brahe's data, they emerge naturally. Automatically. From Newton's single force law combined with inertia, one equation. 3 laws explained. The moon. Why does it orbit Earth? Same principle. It's falling toward Earth constantly, but moving sideways fast enough to keep missing. It falls around Earth instead of into it. The same thing Galileo's rolling ball would do on a curved surface. And the apple. Why does it fall from the tree? Earth attracts it. Same force. Same law. Just a different scale. Newton did a beautiful calculation. He figured out exactly how much the moon's path deviates from a straight line every second, how much it falls toward Earth. Then he calculated how much objects fall at Earth's surface. 1 second. 9 meters. The numbers matched. Perfectly. When you account for the distance, the force pulling an apple from a tree is the same force holding the moon in orbit. Heaven and Earth, same physics. Same law. Same universe. Newton published this in 1687, the Principia Mathematica. One book, 500 pages. That unified heaven and earth. With Newton's law, everything made sense. And it kept making sense. For 200 years. Ocean tides, Newton explained them. The gravitational pull of the moon, stretching Earth's water toward it on one side, and away on the other. 2 high tides a day. Predicted. Confirmed. The shape of the Earth itself? Not a perfect sphere. Newton calculated that Earth's rotation should make it bulge at the equator slightly wider than it is tall. Decades later, French expeditions measured it. He was right. Comets? Edmund Halley used Newton's laws to predict that a comet seen in 1682 would return in 1758. Halley died before he could see it. The comet came back. Right on schedule. We still call it Halley's Comet. Jupiter's moons? Ole Romer noticed that their eclipses arrived early when Earth was closer to Jupiter and late when Earth was farther away. The timing differences calculated using Newton's orbital mechanics gave humanity its first measurement of the speed of light. Lambai Isheror. 0.000 kilometers per second. Not perfect by modern standards, but extraordinary for 1,676. And then the triumph that silenced every remaining skeptic. In 1846, astronomers noticed that Uranus wasn't following its predicted orbit. Something was pulling it off course. Using nothing but Newton's equations, 2 mathematicians, Urbain Le Verrier and John Couch Adams, calculated exactly where an unknown planet must be hiding. They pointed a telescope at that spot. Neptune was there. A planet discovered not by looking, but by calculating. Newton's law didn't just describe the universe. It predicted parts of the universe nobody had ever seen. 200 years. 0 failures. But there was something strange hiding inside Newton's own equations. Something Newton noticed but couldn't explain. Something everyone else ignored. Pick up a hammer. Pick up a feather. Hold them at the same height. Drop them. The hammer hits first. Obviously. Air resistance slows the feather. Now remove the air. Vacuum. No resistance at all. Drop them again. They hit at exactly the same time. A hammer heavy, dense, massive. A feather almost weightless. Same height. Same speed. Same time. Every single time. Apollo 15. August 1971. Commander David Scott stood on the surface of the moon, no atmosphere, no air resistance, and dropped a hammer and a falcon feather. Side by side, they hit the lunar surface at exactly the same instant. This is strange. Much stranger than it looks. Here's why. In Newton's physics, mass does 2 completely different jobs. Job 1, gravitational mass. This determines how strongly gravity pulls on you. More gravitational mass, stronger pull. This is what makes the hammer heavier than the feather. Job 2, inertial mass. This determines how much you resist being accelerated. More inertial mass, harder to get moving. This is what makes the hammer harder to push across a table. These are 2 completely different properties. There is no obvious reason they should be related at all. Gravitational mass is about attraction. Inertial mass is about resistance. Different concepts. Different definitions. Different measurements. But they're equal. Always. Exactly. The hammer has more gravitational mass. Gravity pulls it harder. But it also has more inertial mass. It resists that pull more. The 2 effects cancel. Perfectly. Every single time. That's why everything falls at the same rate. Not because the force is the same, it isn't. The hammer feels much more force. But its resistance is proportionally greater. Force and resistance always in perfect lockstep. Scientists have tested this equality to 15 decimal places. Still perfect. No deviation. Not even a hint of one. Newton saw it. He tested it himself with pendulum experiments. And he had no explanation. In his framework, it was just a coincidence. A cosmic accident. 2 completely unrelated properties happening to match with unlimited precision. Or was it a coincidence? What if gravitational mass and inertial mass aren't 2 properties that happen to be equal, but the same property? What if they're equal because they have to be, because the universe couldn't work any other way? That question, that single question, is what led Einstein to his greatest discovery. Einstein wasn't in a university when he figured this out. He was a 26-year-old patent clerk in Bern, a nobody in the physics world. No lab, no funding, no colleagues who took his ideas seriously. And he was thinking about what would happen if you fell off a building. Not as a tragedy, as a physics question. What would you feel? What forces would act on you? He later called it the happiest thought of my life. It took him 10 more years, 10 years of wrong turns, failed equations, and near breakdowns to turn that single thought into a theory. From 1905 to 1915, a decade of rebuilding physics from the ground up. And here's the thought that started it all. You're in a closed room. No windows. No way to see outside. You feel your normal weight pressing you into the floor. Question: are you on Earth? Or are you in a rocket in deep space, accelerating upward at 8 meters per second squared? Drop something. It falls to the floor. In both cases, throw a ball horizontally. It follows a curved path. In both cases, stand on a scale. Same reading. In both cases, there is no experiment you can perform inside that room that will tell you the difference. Known. Not with any instrument. Not with any level of precision. The physics is identical. This is the equivalence principle. And it changes everything. If you truly cannot tell gravity from acceleration, if no experiment in the universe can distinguish them, then maybe they're not two different things. Maybe what we call sitting still in a gravitational field is actually a form of acceleration. And that leads somewhere extraordinary. Objects in free fall have no force acting on them. Think about that carefully. The falling apple, the orbiting moon, satellites circling Earth, astronauts floating in their capsules. None of them experience any force. Zero. Nothing pulling. Nothing pushing. They're moving naturally, following their natural paths through space and time. No force. No pulls. Nothing acting on them at all. They're not being forced to move. They're free. But the apple is clearly falling. It's accelerating toward the ground at 8 meters per second squared. How can that be no force? What if the apple isn't accelerating at all? What if it's following the straightest possible path, and it's space itself that's curved? This is Einstein's profound insight. Gravity is not a force between objects. Gravity is the curvature of space and time. Massive objects don't pull on other objects. They warp the space around them. They bend it, curve it, distort the very geometry of reality. The apple isn't being pulled to the ground. It's following the straightest possible path through curved space-time. But space-time near Earth is curved. So straight, the most natural path through space and time points toward Earth's center. You standing on the ground right now. You're trying to follow your natural path through curved space-time, a path that leads toward Earth's center. But the ground is in your way. The ground pushes you upward, prevents you from following that natural path. That's what you feel as weight. Not gravity pulling down. The ground pushing up, deflecting you from your natural trajectory through curved space-time. Einstein published his field equations in Annalen der Physik, November, Smilendens Lima Blas. 10 years of work from that happiest thought in a patent office to one paper that redefined reality. And he made a concrete prediction. If gravity is really curved space-time, then light should be affected too. Light has no mass. In Newton's theory, gravity shouldn't affect light at all. But if gravity is curvature of space itself, then light, following the straightest path through curved space, should bend. He calculated exactly how much starlight should bend passing near the sun. Not a vague prediction. A precise number. A number that was different from what Newton's theory would predict, even if you tried to give light an effective mass. Einstein's prediction was almost twice Newton's. In 1919, during a total solar eclipse, British astronomer Arthur Eddington led expeditions to measure the positions of stars near the sun's edge. The stars appeared displaced from their true positions. The starlight had bent, passing through curved space-time near the sun. The measurement matched Einstein's prediction. Not Newton's. Einstein's. Headlines around the world. Revolution in science. New theory of the universe. Newton overthrown. A patent clerk's decade-long obsession, confirmed by starlight bending around the sun. This is gravitational lensing. And we see it everywhere now. Massive objects bending light from more distant objects behind them, creating distorted images. Arch. Rings. Direct evidence visible. Measurable. Photographable. That space itself curves in the presence of mass. Everything your physics textbook taught you about gravity as a force, the arrows pointing down, F equals m times g, memorize it, test on Friday. All of it was a simplification. A useful one, but a simplification. The real answer is geometry, the shape of space-time itself. And you can see it right now. Above your head, astronauts on the International Space Station. Floating, drifting, weightless, zero gravity. That's what everyone calls it. Wrong. The ISS orbits at about 408 kilometers above Earth's surface. At that altitude, Earth's gravitational pull is roughly 90% as strong as it is on the ground. 90%. The gravity up there is almost the same as the gravity down here. So why do they float? Because they're falling. The station is falling. The astronauts inside are falling. Everything, the equipment, the water droplets, the floating pens, all of it falling together at the same rate toward Earth. But they're also moving sideways. Fast. Archibald. 000 kilometers per hour. So fast that as they fall toward Earth, the Earth curves away beneath them. They keep falling. Earth keeps curving. They never hit the ground. Falling forever. Landing never. And because everything falls together at exactly the same rate, there's no relative motion between the astronaut and the station. Nothing pushes against them. No floor pressing up. No contact force at all. They feel nothing. Not because gravity is gone, but because nothing is resisting it. This is equivalence in action. Einstein's thought experiment, the closed room, the falling observer happening in real time, 408 kilometers above your head. At doazitshi opt, 000 kilometers per hour. But here's a question most people never think to ask. Why is Earth round? Not roughly round. Not sort of round. Nearly perfectly spherical. Why? Because space-time curves equally in all directions around mass. Not just downward. Not just toward the center. In every direction. Equally. Take all the matter that formed Earth billions of years ago. A cloud of dust and rock. Gravity pulled it together. But gravity doesn't have a preferred direction. It curves space-time symmetrically. So matter collapses symmetrically. From every direction. Into the most symmetric shape possible. A sphere. Now picture an ant on the surface of a basketball. The ant walks in a perfectly straight line. Never turns. never deviates. Just walk straight ahead. What happens? It goes all the way around, comes back to where it started. The ant thinks it's walking straight, but the surface is curved. The straight path wraps around. This is exactly what's happening in spacetime. Objects moving through curved spacetime follow the straightest possible path, what physicists call a geodesic. They're not turning, not being pushed, not being pulled. They're going straight. But straight through curved spacetime looks like a curve to us. An orbit, a falling apple, a moon that never lands. Space is curved. And time is curved too. Both of them. Together. The more mass, the deeper the dimple. The closer you are, the steeper the curve. Now here's where everything comes together. The moment that separates Newton from Einstein. The deepest difference. Stand on the ground. Feel your weight. Newton says, 2 forces. Gravity pulls you down. The ground pushes you up. They balance. You don't move. Equilibrium. 2 forces. Perfectly canceling. Einstein says 1 force. Just one. The ground pushing you up. That's it. That's the only force acting on you. Weight. If there's only one force pushing upward, then by Newton's own second law, you should be accelerating. F equals m times a. One unbalanced force. You should be accelerating upward. And you are. Not through space. Through space-time. The ground is accelerating you away from your natural geodesic, that freely falling path through curved space-time. Every second you stand here, the ground deflects you from where space-time wants you to go. You feel that deflection as weight. Think about an apple on a tree. The branch pushes the apple upward, holds it in place. 1, force the branch pushing up. The apple wants to follow its geodesic, its natural path, through curved space-time which leads toward Earth's center. But the branch won't let it. So the apple hangs there, held in place by 1 force, accelerated away from its natural path. Then the branch breaks, and the apple is free. No force, no push, no pull, nothing acting on it at all. It follows its natural path through curved space-time, straight toward the center of Earth's space-time well. We call that falling. But falling isn't something that happens to the apple. Falling is what happens when you stop doing something to it. Stop pushing. Stop holding. Stop deflecting. Falling is the natural state. Standing still requires a force. Read that again. Falling is the natural state. Standing still requires a force. That's Einstein's revolution. Not a new formula for gravity. Not a correction to Newton's numbers. A complete inversion of how you think about motion, force, and reality itself. Newton, you need a force to make things fall. Einstein, you need a force to make things stop falling. Everything you feel right now, your weight in the chair, your feet on the floor, the pressure against your back, all of it is one force. The ground, the chair, the floor, pushing you, accelerating you away from your natural state. Your natural state is free fall, weightlessness. The astronauts on the ISS aren't in a special condition. They're in the default condition. You're the one being interfered with. That changes everything. Not just physics. How you experience this moment. Right now. The weight you feel isn't gravity pulling. It's reality pushing. And it has been every second of your life. And Einstein's curvature doesn't stop at everyday experience. Push it further. Much further. And reality becomes something almost unrecognizable. A star. Take our sun. A ball of gas, hydrogen, and helium held in a delicate balance. Nuclear fusion in the core pushes outward. Gravity space-time curvature pulls inward. Two pressures. Perfectly balanced. For billions of years. But fusion fuel runs out. When a massive star 8 times our sun or more exhausts its fuel, the outward pressure vanishes. Nothing fights the inward curve. The core collapses. In less than a second, what's left is a neutron star. All the matter of a star compressed into a city. Roughly 20 kilometers across. The mass of the sun packed into something the size of Manhattan. 1 teaspoon of neutron star material weighs roughly 1 billion tons. 1 billion. Tone. In a teaspoon. Space-time around a neutron star is curved so severely that light itself bends visibly. You could see the back of the star while looking at the front. The curvature wraps light around. But there's something beyond even that. If the collapsing star is massive enough, roughly 25 times the mass of our sun, nothing stops the collapse. Not nuclear forces. Not quantum pressure. Nothing. The matter crushes past every known limit. Space-time curves so sharply that it folds in on itself. Every path, every geodesic, every possible trajectory through space-time leads inward. Even light, following the straightest path through curved space-time, curves back inward. Can't escape. A black hole. Not a hole in space. Not an object sucking things in. A region where space-time is so curved that outward no longer exists as a direction. For decades, these were theoretical. Predictions of Einstein's equations that many physicists, including Einstein himself, doubted could exist in nature. Then the evidence arrived. September Impot Bless. 2015. The Laser Interferometer Gravitational Wave Observatory LIGO detected ripples in space-time itself. 2 black holes, 3 billion light-years away, spiraling into each other. The collision released more energy than all the stars in the observable universe combined. For a fraction of a second, the signal matched Einstein's predictions. Exactly. April 2019. The Event Horizon Telescope, a network of radio dishes spanning the entire planet, released the first image of a black hole. M. Lapantu, 55 million light-years away. A shadow surrounded by a ring of superheated gas, bent by space-time curvature so extreme that the math barely handles it. Einstein's equations predicted what that image would look like, before anyone had the technology to capture it. Published in 1915. Confirmed in 1919. Confirmed again in 2015. And again in 2019. A century of predictions. A century of evidence. Every test passed. Every prediction confirmed. And the most extraordinary prediction of all, that space-time itself can curve so completely that nothing escapes photographed. Directly. By humanity. And it all started with a question you thought you knew the answer to. What is gravity? You've now seen the real answer. Not the textbook version. The real one. Tycho Brahe watched the sky for 20 years, no telescope. Just brass instruments and obsessive precision. Kepler inherited that data and threw out his own theory when the numbers didn't match. Galileo rolled balls down ramps and discovered that motion, not rest, is the natural state of the universe. Newton unified heaven and earth with one equation. Predicted tides. Predicted comets. Predicted a planet nobody had ever seen. 200 years. 0 failures. And then Einstein, a 26-year-old patent clerk with no lab, no funding, no colleagues who took him seriously, asked what would happen if you fell off a building, and spent 10 years turning that single thought into a revolution. Gravity is not a force. Gravity is the curvature of space and time. The apple isn't pulled to the ground. It follows the straightest path through curved space-time. The moon isn't pulled into orbit. Its falling freely has been for 5 billion years. Never landing. The astronauts on the ISS aren't floating in zero gravity. They're in free fall, the default state of the universe. And you standing right now, sitting in your chair, feeling your weight, you're the one being pushed. The ground beneath you is the only force, deflecting you from your natural path. Every second, your entire life. Falling is the natural state. Standing still requires a force. That's not a metaphor. That's what Einstein's field equations say. That's what the 1919 solar eclipse confirmed. That's what LIGO detected in 2015. Ripples in space-time from black holes colliding 3 billion light-years away. That's what the Event Horizon Telescope photographed in 2019, a shadow of curved space-time so extreme that light cannot escape. And that's what your GPS corrects for every single second. Einstein's equations predict that clocks run faster in weaker gravity. The satellites orbiting above you tick 38 microseconds faster per day than clocks on the ground. Without that correction, without Einstein, your maps would drift 10 kilometers daily. Your phone depends on general relativity. Every day. Right now. Published in 1915. Confirmed in 1919. Confirmed in 2015. Confirmed in 2019. Confirmed every second by your phone. A century of evidence. Not a single failure. This is what your physics textbook didn't tell you. Not because they lied, but because the real story takes 35 minutes and most people never hear it. You just did. If this changed how you see gravity, if you'll never feel your weight the same way again, hit subscribe. I make videos like this regularly, taking the deepest ideas in physics and making them feel real. Not dumbed down. Real. Leave a comment. What surprised you most? The floor pushing up? The moon falling for billions of years? The teaspoon that weighs 1 billion tons? I read every single comment. And if I got something wrong, tell me. Sources are in the description. I'd rather be corrected than comfortable. Next video, we're going deeper. Into the quantum world, where even Einstein's beautiful geometry starts to crack. I'll see you there.